In this video, I want to talk about a special circuit using Laplace analysis because it's one that's used in energy storage applications. The pulse power guys use this. It's also kind of a prequel to talking about filters and RLC filters. And you skipped over it in circuits because to actually represent this in circuits is a second order differential equation. Most people who are taking circuits have not yet had differential equations, so we don't really cover the RLC. So what I want to do is just kind of go over RLC circuits, and we will start with the series RLC circuit. The parallel one is solved in quite a similar way. So what we're going to do is we're going to have this capacitor, and it's got some initial voltage on it, V sub 0, and it's storing some energy. And then what we're going to do is we're going to utilize that energy by switching that capacitor to an RL circuit. So we've got this capacitor, it's got an initial voltage. We're going to switch it at t equals 0 onto this LR combination. And then what we're going to be interested in is for t greater than 0, obviously we're going to have some current flowing and some voltage here across the resistor. So just to talk about why this particular example, this is pretty representative of some physical circuits that you see in use. Capacitive energy storage is more commonly used than any other kind of energy storage if you're trying to create some kind of transient circuit that's going to deliver a short-term pulse. So this would be very representative of a system where you have some energy stored. It's stored in a capacitor bank. You then want to switch it off onto some kind of load. Usually that load is something that requires a pulse, and so you want to basically just deliver all that energy that's stored in the capacitor into a load that is typically a resistive load. The inductance physically is usually modeling inductance in the actual physical circuit. Sometimes an actual inductor is wound so that you can determine the behavior characteristics. Other times the inductance is just what you have in the physical system. And so as we look at the response of this circuit, you'll understand from a design, and as I said, the most common application of this would be in a pulse power kind of configuration where you have some energy stored. You maybe take a long time to charge the capacitor, and then you want the energy released over a shorter period of time into the load, and so you're getting a power gain out of this by doing this. In actuality, in pulse power, this is usually the first stage in several power conditioning stages where they tend to get higher and higher peak power and shorter pulse duration. So a lot of times this is just kind of the initial power conditioning that then feeds maybe something else that shortens the pulse even further. But the fundamental thing of storing energy capacitively is fairly common. Capacitors are cheap. They can be built with very low leakage, and so you can hold this DC voltage for a while on that capacitor and then release it. All right, so let's look. If we take this circuit and we look, obviously we've already given you an initial condition, and I'm going to work with RLC and V. I'm going to work with the variables, not numbers, because to me, if you use realistic values for the numbers, you've got too many exponents running around. So we'll just work this out generically, and then you can see how that works when you substitute actual values. So if we take this circuit then and we transform it to the Laplace domain, we get 1 over SC for our capacitor. We get a series voltage source, V naught over S. The switch is closed. The inductance becomes SL. The resistance remains R. The current is, and if you don't mind, I'm going to drop my subscripts and just use I of S, and the voltage across the resistor is going to be V of S. So this is my circuit. So I can write a simple mesh equation, minus V naught over S plus 1 over SC times I of S plus SL I of S plus R I of S. And then doing some simplification, I of S times SL plus R plus 1 over SC is V naught over S. And then if I solve for IS, I get V naught over S, SL plus R plus 1 over SC. And then doing some additional simplification by multiplying through by S squared L plus SR plus 1 over C. And now remember the cardinal rule about working in the Laplace domain is we look at our denominator and we look at our highest order in the polynomial, and we want it to have a coefficient of 1. So I want to multiply numerator and denominator by 1 over L. And that gets that S squared to have a coefficient of 1. Which gives me the following equation for the current. Okay, so now let's look and see what happens when we try to take the inverse transform of this. So in the numerator is just a constant, the denominator is a second order polynomial. So we have, if we want to solve for the roots S1 and 2 would be minus R over L plus or minus the square root of R over L squared minus 4 times 1 over LC, and all of that will be over 2. So now I'm going to take the 2 up, so my roots will be minus R over 2L plus or minus the square root of, now when I take the 2 in the denominator into the radical, both of these are going to be over 4. And then when I take it into the bracket here, that's squared, it's going to go back to R over 2L squared. And then the 4 will cancel in that second term, and I'll just get this. Okay, so what that means is I of S, and I'm calling this S1 and 2, I of S is V naught over L over S plus S1, S plus S2. So what are S1 and S2? Well, they're dependent on R, S1 and 2, which are the poles. Its functional form depends on R, L, and C. So if R over 2L squared is equal to 1 over LC, then the term under the radical goes to 0, and I have a double pole where S1 and 2 are both equal to minus R over 2L. And so that would be a general solution of the form I of t is some constant e to the minus t over tau plus another constant t e to the minus t over tau. Okay, because we have that degenerative solution. So that's the case where these two are equal. The other situation is if R over 2L squared is greater than 1 over LC. Okay, in that case, the term under the radical is real. Or is positive. giving us two real distinct roots, which would give us S1 is equal to some alpha and S2 is equal to some beta. Okay, just picking some constants, which would be a general solution. I of t is some a e to the minus alpha t plus some b e to the minus beta t. Okay, this is the situation where in your multisim model was what we called overdamped. You get a rise and a slow decay. This one was what we called critically damped. And then finally, the third case is if R over 2L squared is less than 1 over LC. In that case, you have a negative term under the square root sign. That would mean that you would have two poles, and they would be complex conjugate pairs. Some sigma plus j omega and sigma minus sigma plus j omega and minus sigma minus j omega. And so your solution would be of the general form I of t is a e to the minus sigma t sine omega t plus b e to the minus sigma t cosine omega t. This is the